are times when the inevitable end of life as we know it becomes the greatest mystery of all. And even for a star, old age involves many changes.
Stars, those faint points of light that we see in our nighttime sky, are actually great globes of glowing gas. Kind of sounds like an oath. But in any case, these huge hot spheres of gas, with temperatures of tens of millions of degrees in their cores, are gigantic natural thermonuclear reactors, which through fusion are able to shine and so balance against the force of gravity that's constantly pulling inward. The same gravity, in fact, which first prompted the stars to condense out of the diffuse clouds of interstellar gas and dust. And as the stars convert hydrogen into helium through this process, they remain in the main sequence phase of their lives. This is a very stable period, stable in size and in brightness. But stars don't last forever. They're consuming their own material in a constant battle against gravity, which they must eventually lose because they run out of fuel. And so they must change. And there are several different ways that once a star runs out of fuel, it can leave the main sequence part of its life, and the exact course it takes depends upon the mass of the star. But today we're going to be considering stars that are not so massive, stars like the sun. And this isn't very pleasant, but the sun will eventually run low on fuel. And when this happens, it will swell into a gigantic red giant star, the largest of all the stars. And in fact, the sun will be 1,000 times larger than it is now. Well, these red giants are seen elsewhere because other stars have gone through this process. And these objects then are the most conspicuous indicators of old age among the stars that we can see.
Most stars can be arranged by their surface temperature and intrinsic brightness into a continuous series called the main sequence. The bright blue giants lie at one end of the sequence, the dim red dwarfs at the other. Off this main sequence, there are some enormous red giants, and as their color indicates, these are cool stars. They may have started as bright blue stars, and in an evolutionary process of aging, their surfaces cooled and they eventually swelled to their enormous sizes. Most stars shine with a constant brightness because there is a balance between the force of gravitation that acts to contract the star and an elastic or pressure force that acts to expand it.
The main sequence phase of stellar evolution is the longest and most quiet phase. The star is converting hydrogen into helium, and the thermal energy produced in this way maintains the balance against the gravitational contraction. Now, hydrogen is a very efficient fuel, and also the star has a tremendous storage of hydrogen. However, only about 15% of its hydrogen can be actually used in this way, because the condition is that it can be converted only in very hot regions near the star center. So after a definite time, all hydrogen must be exhausted, and that is the end of the main sequence phase.
An HR diagram can be used to illustrate the evolution of a star like our sun. Having first formed as a young proto-sun and then lived out its lengthy main sequence existence, internal changes begin to transform the sun into a red giant. For a time, the surface of the sun will boil from hydrogen burning and will increase in brightness. But as the chemical composition changes from hydrogen to helium and the nuclear fires begin to fade, the core will collapse. In response, the outer diameter increases and the surface temperature decreases. 80 million years after leaving the main sequence, the Sun will change violently and expand 200 times, engulfing Mercury, Venus, and Earth. The helium will finally ignite in what astronomers call a helium flash. With the change of fuel, strange things may happen. Like more massive stars, the Sun could become unstable. It could pulsate and be known as a variable star. There are many other types of variables. Some pulsate once a year, others in a few seconds. Once past the variable stage, the Sun will become brighter still, 10,000 times brighter than our present Sun, and expand 300 times larger. It will have reached its maximum size, becoming a red giant.
When stars evolve across the HR diagram, they pass through a region known as the instability strip. In this region, the envelope of the star is pulsationally unstable, and the star will physically pulsate, change in size. When it does this, its luminosity, at least the luminosity in the visible region, will change in a very regular manner. A classical example of this type of star is the Cepheid variable. These stars have proved very useful in astronomy. In stellar evolution, we can look at the period, the luminosity of the star, and from this information we can get a handhold on what the exact helium and metal composition of this star is, and also gain some knowledge of what the current mass of the star is. In regions other than stellar evolution, the Cepheid variables have proven extremely useful as a standard candle. It's been discovered that there's a very precise period luminosity relation, such that a longer period star has a higher luminosity. So when we look at one of these stars, we know how bright it is. It can then be used as a standard candle to determine distances to objects such as other galaxies.
There are irregular variable stars which change in brightness in seemingly random fashion in a day, a month, or a year. But there are also stars that are predictable, varying in brightness regularly or periodically. This star, for example, called an RR Lyrae star, changes its brightness regularly in periods of several hours, year after year. Despite the fact that the RR Lyrae stars are several times larger than our own Sun, they're regarded as small members of the family of regular variable stars. There are also larger periodic variable stars called Cepheids that change in brightness regularly in periods of days. Cepheids are about 100 times larger than our Sun. The largest periodic variables in the sky are called Miras. These stars change in brightness regularly over periods of months. The cause of these changes in brightness is a physical pulsation, an alternate swelling and contraction in a rhythmic manner under the opposing forces of gravity and gas pressure, which are never quite in balance, as is in a normal star like the Sun. This pulsation occurs over and over again for thousands and thousands of years. One of the most amazing properties of these regular variable stars is the beautifully simple relationship between intrinsic brightness and a period of pulsation. The larger, brighter stars have longer periods than the smaller, fainter stars. Because of this period luminosity law, it's possible to determine the intrinsic brightness of a pulsating star, which provides its distance from a simple knowledge of its period of pulsation. Because changes in the brightness of many variable stars are noticeable and measurable even with small telescopes, the observation of such stars is one area in which amateur astronomers have been able to make major contributions to astronomy.
There are people who work for an organization called the AAVSO, the American Association of Variable Star Observers. They're based in Cambridge, Massachusetts. And you can, with a little experience, establish brightnesses of stars, magnitudes of stars, by comparing them to stars with known magnitudes. This is a program quite a few people are engaged in and have been for many, many years. It's an international endeavor. And the findings that you make as you watch variable stars, because stars vary in brightness, these findings, properly noted, are then returned periodically to Cambridge, and they are charted today by computer, and they give professional astronomers a great deal of information about the behavior of variable stars, which they themselves, the professional astronomers, do not have time to make. These observations best done by amateurs. And the Problicom program, of course, which works with very nominal equipment, equally employs the time and talents of amateurs with very, very little investment by using plain photography to achieve similar ends. In fact, the American Association of Variable Star Observers has now asked me to participate in their NOVA search program, which is a part of the AAVSO. NOVA being a variable star, the very fact that it explodes makes it a variable. It varies very quickly, in fact, when it first bursts into view. The Problicom program is, I feel, a program, the time of which has come, and one that addresses itself particularly to the beginning amateur who doesn't know what's there and what should be where, but who can, by just noticing something new, then find out what it is, get counsel, and make potential discoveries.
Today, almost any reddish star seen in the night sky is a red giant. Antares, in the constellation Scorpius, probably was much like our sun at an earlier time in its evolution. But in becoming a red giant, Antares increased its volume to some 60 million billion times the volume of our sun. A star becomes a red giant when the hydrogen in its center becomes depleted, causing the core to collapse under gravitational pressure. The energy produced during this collapse radiates outward, causing a phenomenal expansion of the outer part of the star. But even the red giant phase is not the last phase of a star's life.
The star leaves the giant region essentially in two ways, either peacefully or violently. The peaceful end of its life is a contraction to a white dwarf. The violent end is more complicated. The star gradually exhausts all resources of energy it has. Then it begins to collapse suddenly, but the heating of the innermost layers is so strong that the star eventually explodes in the form of a supernova, throws most its material into space, and the remnant becomes a neutron star or a black hole. Now the decision which way it will take depends on its instantaneous mass. If the mass is sufficiently small, smaller than about 1.4 solar masses, it will become a white dwarf. If the mass is larger, then the star should in principle explode. However, it is possible, and in most cases it probably happens, that before the decision is made, it can shed most of its material, so actually probably stars up to, say, 7 solar masses can still become white dwarfs, provided they manage to get rid of most of their material at the red giant stage.
When, as a red giant, the sun's supply of nuclear fuel is eventually exhausted, and the temperature at its core is insufficient to release more energy through the fusion of still heavier elements, the sun finally loses its relentless battle against gravity. Decreasing in size and in brightness, the sun will enter its last phase and become a small white star. Only 1/100th the size of our present sun, this white dwarf will begin the long, slow process of burning out. Nearly invisible, it will wander through space. The only energy remaining is that which formed it, gravity.
You know, in many public lectures, my colleagues usually call white dwarfs dead star. I think it's unfair. They are simply retired stars. They no longer produce new energy, but they have kept enough of heat inside. Now they are much thriftier in emitting that than before. Therefore, they gradually cool off. They also gradually become fainter and fainter, but at this stage they can live for tremendously long ages, for billions of years. And they gradually become less white and more reddish or gray and so on. In the end, they must be really dark stars, very cold, emitting no light, but they are still there. Nothing can, as far as we know, nothing can destroy them. But their lifetime may well be longer than the lifetime of our whole stellar system.
Some stars do something very pretty as they evolve. They become planetary nebulae. This is a peculiar and odd name, and it's an indicator when these objects were first discovered, they really weren't recognized for what they truly are. In the late 1700s, after William Herschel had discovered the planet Uranus as a small greenish disk in his telescope, an appearance which was matched closely by the planet Neptune, discovered about half a century later, well, astronomers combed the sky looking for more of these small blue-greenish disks in the hopes of finding more planets. Well, they found quite a few of the blue-green disks, but they didn't find many more planets at all. And they realized fairly soon that the disks that they did find weren't planets. They actually looked more like clouds of gas or nebulae in space. They didn't move like planets either. Still, there was this superficial resemblance to Uranus and Neptune, and so these objects were called planetary nebulae, even though they have absolutely nothing to do with planets. They're actually bubbles or shells of gas that have been gently thrown off by stars of low mass late in their lives as a kind of a final gasp before cooling off and fading. These planetary nebulae have picturesque names, too. Names like the Ring Nebula, the Helix Nebula, or the Dumbbell. And they clearly look like bubbles or smoke rings with the remnant of a star in the center that is a collapsed, dense heap.
A planetary nebula is probably exactly the case when a star originally has an excess mass for a white dwarf, but manages to shed it at the stage of a red giant. If you imagine a star which is not too massive, say like our sun, or 2 solar masses or 3 solar masses, when it has expanded to the giant and red giant stage, it's an enormously expanded star, which if it were in the place of our sun, it would actually have its surface beyond the orbit of Mars, say. It's natural that the gravitational attraction of the star upon its surface is really not too strong when the star is not too massive. It's possible that the outer layers can escape into space. If they are blown away into space, but not too violently, they can form a shell surrounding the star, a shell of gas, which is visible for some time as a planetary nebula. Planetary nebula is a relatively peaceful release of the outer envelope of a star into space. What's left is the central hot star. In fact, it's already a ready-made white dwarf sitting there inside a giant star. Now, it must cool off a little bit, so there is still a certain evolution, but gradually, probably the central stars will be transformed into ordinary white dwarfs.
The planetary nebula phase through which some stars pass is a very brief phase, lasting only a few tens of thousands of years. The planetary shell provides one means by which a star can shed some of its mass and evolve from a red giant into the final stage of its existence as a white dwarf. A more complex but equally interesting situation arises when a star is orbited closely by another companion star. Then it's actually possible for gaseous material to be passed from one star to the other.
When a star has another star very close to it, in other words, if it is a double star, or as we say most of the time, binary star, there is an important limit imposed on its expansion. As I already said, each star tries to expand into a red giant. But a star close to another star cannot well do that because the gravitational attraction of the other star will soon overpower the gravitational attraction of the star upon itself, and material will begin to flow from our expanding star to the other star. So in a binary star, stellar evolution is considerably changed because there is mass transfer, mass exchange between these two components. It can then happen that a star which originally was more massive than its companion will end up as the less massive star because a considerable part with mass has been transferred to the other star. Such a star is, for example, Algol in the constellation of Perseus.
Associated with binary stars are eruptive stars called novae. The sudden appearance of one of these eruptive stars is signaled by a rapid rise in brightness amounting to tens of thousands of times in a few hours. A slow decline in light may then persist for a year before the star settles down to its former obscurity.
We believe that a nova is actually a binary star with two components very close to each other. One of them is probably a white dwarf. Material flows from the other star to the white dwarf, but the white dwarf has a very peculiar structure. It cannot accommodate the inflowing material very easily. Rather, after a little bit of it has accumulated at the surface of the white dwarf, there is a violent eruption, and the material is thrown into space. And this outburst is observed as the outburst of a new nova star.
The question of how many times a nova can explode is a very interesting one. Before we did some recent work on the Andromeda galaxy, the answer that you would find in a textbook or a discussion of novae, or the sort of the answer that would be in most people's thinking, is that a nova, a classical nova, explodes only one time. We have been able to identify a class of dying stars in the center of the nearby Andromeda galaxy. And in the course of a discussion with one of my graduate students, Chris Price, the question came up of whether or not we could be confusing any of the stars that we thought were dying through the planetary nebula stage with novae. And as a result of this question and some consideration of it, I realized that if we compared the number of novae in Andromeda to the rate at which stars were dying, we might be able to say something about the number of times a nova explodes. And the reasoning is fairly straightforward, and it goes like this. Let us suppose, for the moment, that every dying star becomes a nova. And let us then suppose that a nova only explodes once. Then when I compute the death rate in the central regions of Andromeda under these assumptions, the nova rate should be exactly equal to the death rate. But suppose now that when I compare the frequency of novae to the rate at which stars are dying, I find that there are 100 times more novae per year than there are dying stars. Then that would say that if every star that dies becomes a nova, it must explode, the nova then must explode 100 times. Well, when I did the comparison, it was immediately evident that the nova rate greatly exceeds the stellar death rate. I can't make a precise estimate of the number of times a nova explodes because I don't know precisely what fraction of dying stars will be in novae systems. But what I can conclude is that the number of nova explosions will be very large, and that number may be as large as 10,000.
Red giants and white dwarfs, planetary nebulae and novae, and a whole variety of pulsating variable stars are phases and events which seem to be connected with the last 10% of the lifetimes of stars like the Sun. But the more massive stars also become red giants, and many of them, too, go through phases of variability. But their ultimate fate is much more violent, say, than the lovely, delicate planetary nebulae. And their finish, the finish of the massive stars, is briefer than the long, slow cooling of a white dwarf. A massive star is destroyed almost instantly in a titanic supernova explosion, which leaves behind a super-dense and super-mysterious neutron star, or perhaps even a black hole. But just because our own sun's passing will be less flamboyant than that of a massive star, it'll be no less catastrophic to the Earth. Even the slow, peaceful end of the sun will destroy us. At least, however, it won't come as a surprise. We can calculate what the sun's future will be, what the past has been for that matter. And we realize that we're about halfway through the main sequence part of the sun's life, that we've got about another 5 billion years before the sun becomes a red giant. When it does so, at the surface it'll become cooler, but it will still be hot enough to vaporize most materials, and the overall brightness of the sun will be greater. And as the sun expands, the oceans will boil, and the air, our atmosphere, will evaporate off into space, and the ground beneath our feet will melt. And altogether, the Earth will not be a very pleasant environment. Well, there was once a lady who approached an astronomer who was giving a talk on the future of the sun, the evolution of stars, and what that means to the Earth. And after the talk was over, she said, "Professor, how long did you say it will be until the sun will destroy the Earth?" And the astronomer answered, 5 billion years. And the lady replied, "Oh, that's a relief. I thought you said 5 million.